what I'll be elaborating, I'll try to make this brief, but it's a series of papers by Eijnden and Song that themselves build on other things with score-based learning, right? And so this has evolved into something which I think now is at the core of the generative models that are being used, for example, in DALI or all of the the most fancy way you can do these images, right? And I'm going to make a connection into the way. So if you go through their papers, like often, like it's a bit of a work in progress at the beginning. And so there are steps, and then the story crystallizes. And so I'm going to give you the sort of the end of the story, but not even necessarily from their viewpoint. So it's more my take on it. And so you remember that what we wanted to do is that there was this idea that there is a base distribution rho b, right? And then there's this target rho star. This one is simple, and this one is complex. And we are really here in the context where we have data. So it's not it's like the first class I gave, right? There is data, and what we would like to do, meaning by data, that means samples. We think about that as samples. In the context of images, that just means we have images, okay? And what we would like to do is a generative model, so is to get more samples, right? And so, the idea is to get a connection. And for this lecture, it's going to be easier to think about it in this way, right? A rho t that goes this way. But at the end of the day, we're going to read it either that way or that way. So we're going to try to find a connection in distribution or density space that go from rho star to rho b. And then if we have that, we can read it in reverse. Okay, and that, what does that mean? That means that at the end of the day, what we would like to have, even though this is not the way it's presented in Eijnden and Song, is we'd like to have a V which is such that this is true. The way, and in their case, there will be this thing, which is that it's really at plus infinity that we're going to have rho b. So there's a few things that I will need to explain, but we'll get to that later. Is that before we were saying t equals 0, 1, now it's going to be t going to infinity for a reason that I'm going to explain. Okay? And again, what we would like to find is what is the v that is doing this, right? The idea being that, well, if we can find that, then, I will have that if I take a t which is sufficiently large, and we'll see what that means, I'm going to get something which is approximately equal to rho b, the base. And then if I allow myself, this little error here, I'll take a sample from rho b, which I should really have had taken at infinity, and then I'm going to push it, but I take it at t, and we'll push it back to rho 0, right? So we're going to, this way we would have a generative model. Is that clear? Okay. So their basic observation is to say, well, this problem is hard if I stick to transport which is deterministic like that. But there is something that I could write that's actually very simple that will guarantee that this is true. And it's simply, instead of looking at this equation, right, which is, this is like a Liouville equation. It's just, first order, right, for the physicist. Well, let's go into something else, and let's go into a Fokker-Planck equation. So let's write one, right? So let's make two choices. Let's say that this guy is a Gaussian, unit Gaussian. So I'm just going to take, I want to have this, right? That's the density that I want to have. In the case of the image, that's really, by the way, what they do. Every pixel somehow is mapped into that. Maybe there's a normalization, but that's really the one that they want to have. And then you notice, you say, but in fact, there is a Fokker-Planck equation that has this density as invariant density, and that's just, the one that corresponds to, essentially, is the Fokker-Planck equation on this potential. if I think about that as a UB of x, right, I can write down the Fokker-Planck equation associated with that, and the Fokker-Planck equation is simply this equation. So there is an x rho t this term being here, this term being simply the gradient of UB of x, in the case that's there, right? And that equation has the property that if I take any initial condition, in particular if I take this, then the limit as t goes to infinity of rho t will be equal to rho star. So it will be equal to rho b. So it has the property, I mean, I'm just repeating at the level of a Fokker-Planck equation what I wanted to have here. That's guaranteed there. Okay? And now you can make two observations. First of all, okay, so let's first realize that in fact this equation I can write like this equation. Because I can rewrite that simply by saying let's write that as the divergence of, well, there is a term which is minus x. I'm going to put a rho t here. And then you simply put, there's a minus. You take the gradient of the log of rho t. You write that. Because, okay, this minus kills this minus, right? This one kills this one. The x rho t, that's the drift term that I have here. Okay? And then the grad, this guy, just to make everything explicit, this is equal to this, but then I multiply it by rho, so they cancel. I have an additional divergence on this gradient, so I get the Laplacian. That's elementary, right? So, of course, this quantity here, right? So this means I can, this is the V that I need, right? This is the V. This, you know, what I've defined here, that's the V that I need to find if I want to make the equivalence between these two equations. In the original paper, they actually didn't think about doing it with transport like that. They were trying to reverse the diffusion. So I'll get to that in a minute. So I think it's more complicated, though it might have some practical advantage. So let's do, you know, do two steps now, which is my key is there. So I want to learn this V, and in fact you realize that the only thing that I really need to learn, you know, we don't need the full V, because the only thing that we need to, this part we already know. What we need to learn is this. Let's call that ST of x. It stands for the score, because it's like the Fisher score in statistics. Okay? And then you can, again, there are many variants on this, but you can write an objective function for this score. So what's the objective function? That's the Fisher divergence. You just say, well, let's imagine that we're in RD. You write this objective. You say, I'm going to and I'll first describe each time the simpler version, and then if you want, we can discuss things that are more complicated. I take this as an objective, okay? And then if I minimize this over ST, right? We will do it all the times at once, but you could do it time slice by time slice. The minimizer here, right, is grad log rho, which is the one that I searching. I could put a little at here to distinguish the variable I'm optimizing upon with respect to the, right? And then you use this identity, which I think, I can't pronounce his name. It's a Finnish guy, which is you expand this. In some sense, in the objective, we're going to undo what we did here, which is there's one term which is, you know, just the square there. Then there is minus 2 times, sorry, the STX There is that, and then there is one more term, which is this. We're almost there. So let me drop the x to go right. Right. The objective that is here is the same as the one that's there. Right? But in this objective, you realize that I can drop this baseline. That doesn't depend on S. Right? So doing that means that now I have lost the ground truth. I know that at this level, if I was able to really evaluate that, I would know that at the minimizer, if I'm doing well, I should get that the objective is 0. If I drop this term, I don't know anymore. But that will allow me, among other things, to use an empirical version of this estimator. And then the next step you do is that you realize that this guy here is the gradient of rho tx. Because the gradient of the log is the gradient of rho divided by rho, and there's a rho. So, okay? And now you integrate by part. Let me write it here. And what you end up having is RD S at so that's the divergence of S. So you want to learn this, right? The new minimization problem that I'm going to do is this. Minimize over that, right? And then, you know, if I denote the minimizer, right, the argmin would be S star, let's say like that. Well, I can take as Vt of x minus star x. And that's the velocity that I would use here, be done. Okay? And now, so we're almost there, except that we need to think about what to do with this, which is that this is the population loss, and I need to have a way to estimate it, right? But we are in good shape already because, you know, it's an expectation with respect to rho t, okay? But I know rho t, or at least I don't know. Actually, we don't know rho t, but we can sample it. Why? Because this Fokker-Planck equation is in fact the rho t here that satisfies this Fokker-Planck equation is the probability density function of an Oersted-Uhlenbeck process. So if you write this as dE, if you look at this as dE with x at time t equals 0 equal x distributed according to rho star, right? Maybe I can put it with a little x star to make it that it's a sample. Well, actually, let's leave it like that because I don't want to have too many indices. Then the way this would evolve, so the PDF, the probability density function of this process, satisfy this Fokker-Planck equation. So, is everyone familiar with this, or okay? So, well, I said okay, maybe a little bit too fast. You're fine with so in fact, I will. You know, we don't need to think about the SDE. We can just solve it. So let me erase this. Right, it's just the minimizer that we will do. So the solution of this equation is explicit. It says xt is equal to xe to the minus t. That comes from the drift, and that's the initial condition. And then, you know, you use Duhamel principle to solve it. So the solution can be expressed like that. So, and this looks a little bit fancy, but in fact, you realize that this object here, at any so it's a process depending on time, but if at any fixed time, if I freeze a time, this in law, meaning the statistics of this object, is I know I'm probably going to get it wrong. I think it's including the square root of 2, we can make this little calculation. This is 1, the square root of time an n01.
Evolving with a Gaussian,
yeah.
Exponentially decreasing weights.
Right. Let me derive this.
I mean, the squares of these two numbers sum up to 1, which is a good thing, right? E to the minus t squared plus these things squared is 1, which I guess...
Yeah, let me do this little calculation, just because I don't remember if I need the square root of 2 or not, which is that, so this object being, so this is a Wiener process. So since it's a Wiener process, which is Gaussian, this is a linear combination of Gaussian, this is a Gaussian process, I just need to calculate its mean and its covariance. Actually, not the covariance, just the variance, because I want to know what's going on at one time, t. So the mean of this is 0, right? And so if you look at this object, what is the expectation of the integral from 0 to t of e to the minus t plus s dws square, right? This is what I want to do. By Ito isometry, this is the integral from 0 to t of the s and the square of the integrand, right? That's Ito isometry. Okay? If you're a physicist, you would just say that dws prime expectation is a Dirac s minus s prime, then you integrate that, you get that. But you know, okay. And then if you do this integral, if I make no mistake, this is 1 e to the minus 2t, right? And so if with the square root of 2 here, I would have gone on a 2 there, and this guy would be gone, right? And so this says that in law, which is, you know, this quantity is just this, okay? But then that means that if I have data, right? If I have, well, I don't know what to write them. If I have xi, right, I equal 1 up to n, which are samples from rho star, okay? I can create samples. These are now samples from rho t, right? And so, which means that, you know, there's an estimator for this here, which is simply 1 over n, sum from I equal 1 up to n of the s at xit square plus twice the divergence of st.
If you also already have the transport operators, why do you have to work so hard to get the velocities? They don't come out of the transports?
Because okay, so it's okay. It's a good question. What you have here, right, is I have built for you an SDE, okay, this SDE, right, which is with this Fokker-Planck equation. Now this SDE goes forward in time and push rho star towards rho b, but that's not what you want to do. That, in a way, is a bit trivial, what we are doing here, which is just I take my image and I turn it into noise. At the end, I want to turn noise back into an image. So at this level, you could say I'm going to, here everything is simple, because it's deterministic, right? The characteristic equation with this is just an ODE, and ODE are simple, because if I were to know the VT, I can integrate this equation forward or backward in time. No problem. This, I cannot integrate backward in time, right? I would need to, so this equation here, which defines the forward process, is a Markov process. If I read it backward in time, it's also a Markov process. But if you want to write down what it is, you need to know, it's not explicit. You need to know what is the grad log rho. In fact, I think that the reverse is dE. And this is, in fact, what they used in the original. I'll write it here. And that one, so the reverse is dE. And I'm going to, again, no, the time will be going from here to here, but forward. It would be this. Actually, I'm not completely sure of the sign. I think it's a plus, but you need to add minus the gradient of the log of rho t. There is that. Of the x reverse t dt plus the square root of dwt. I'm not completely sure that this is the reversed equation, so I'll put that in quote and we can check later. In fact, what they were proposing to do in the original paper, they were not doing transport like that, no normalizing flow. They were just saying, I'm going to construct this SDE that will, you know, this SDE pushes rho star into the rho B, and then I'm going to turn the image into noise, and then the way we're going to turn noise into images is by reversing the SDE, which means using this equation. But whether you don't avoid the fact that you need to know this, which is unknown to you, a priori. So you still need to learn it. Okay? So they were learning it to put it into the reverse diffusion. Just equivalently, instead of thinking about the reverse diffusion, you can just stay at this level, which is the transport where V is the one that I wrote, right? Is the one that is there, is V, and just integrate that one forward and backward in time. Okay? There are practical considerations why you might prefer to have the SDE. There's a few things that we can discuss later. I think, as a rule, if you can integrate an ODE rather than SDE, you should really go for the ODE, because time discretization is tough.
See, but you have an explicit formula for the transport.
It's not explicit, so now let's think about, right? No, there's one, right? There is one more step, right? Of course. No, what I have explained. We have an objective function which is here. That's the population loss. Now we have an empirical version of this, where these guys are the one that I generate by taking the data and adding to them this noise. This is what is done, right? This box allows me to do that, right? And yeah.
So does the convergence of that estimator depend on t?
So let's get that's right. The S that you have here, I forgot the little at there. The S that you have here, right, is different at every time.
Yeah,
right.
Does it matter, like if I go further out? So I'm curious about this t equal to infinity, and so.
Okay, so let's discuss that now. Okay, which is okay. So. Allow me just to build a few more steps and then we go there. So now there's a question of, there's one more step which is to do, which is how will I learn this, right? The way you learn it is that, well, we're going to parameterize this by, so I'm just going to put a theta. What does that mean? It means that no, this guy is parameterized by a neural network. And instead of minimizing over S, I will minimize over theta. That's right. With respect to what we have done in the previous classes, there's something which is very nice here, which is that you don't need to use this neural ODE business and go forward, backward with the adjoint, because this is completely explicit. The data is there. Okay? You could obviously do that, and that's your question. You could do this at every time slice with one neural network for time slice, but then you would need to discretize in time. So they make another little thing, which is that I can just as well integrate this from 0 to some capital T, which is the final time that I will use it there, right? Well, actually, at this level, I could even do that, if you wish, and then have a dt like this. That, if I just do that, doesn't work, because I would end up putting, okay, so let's think about it. So what I'm going to say is that then you add a weight in time. This is the objective that we're going to use, where the Wt, for example, you could take Wt is e to the minus alpha t for some alpha bigger than 0. Okay? So that's one possibility. Right? And now, the difference with respect to the line that was done before is that I will now think about S. Where can I write this? I don't need the calculation which is there. Instead of having one neural network per time slice and thereby being obliged to discretize in time, we're going to simply parameterize S theta, which is just a neural network that goes, say, 0t, 0. I mean, eventually we need to fix that like that, right? It's a network which is parameterized. So it's a function that does this. It's just a big function that takes as input a tx, right, and output an s hat of tx in RD. Okay, and they do that with UNet, I think. That's the, you know, again, these are the practicalities where we need to go to the paper. It's actually quite tedious. So you do that, and then you realize that, in fact, if, for example, if I take, let's take alpha equal 1, just for the sake of the argument, right? In fact, instead of doing this, I can also evaluate this empirically. Forget about this integral. Forget about this integral. Put the 1 over k, sum from k equal 1 up to k, and then just put tk everywhere, right? And the tk are just distributed according to the exponential that is here. Okay, that's gridless, right? And so now I have a loss in which, in fact, I wrote that like that, but so obviously you can do some form of online learning. There's one thing that's fixed. You're stuck with these guys. That is your data set, right? If you do sampling, like I explained in the previous class, then you could potentially regenerate it. But here, you just have your data that is whatever images you want to train things on, and that's it. But all the rest you can do online. Meaning, if you do stochastic gradient descent, at every step of iteration, you can change your batch of times and change your batches of noises here. You don't need to use the same. Okay? And then you declare this to be, this is your L of theta, and just write it like that, right? You do this. At conversions, what do you get? You get your S, meaning you get your V, and then you can either use it as they were doing it before, which is with this reverse SDE, or you can simply use the SDE which is there, the ODE which is there. Okay? Now, yeah.
So I'm a little confused going from that objective to the empirical one. Especially the weighting factor. Are you guaranteed that the number of samples you have is very large, you will converge to?
Yeah, so they are, I mean, so the one that I really used here is this guy, right? Is this, and then is, right? And then I put the weight here in time, this W. Let's just take the same, so e to the minus t dt. There is a bit of, we can discuss that in a minute, which is what exactly is the weight that I should put there, right? These estimators are consistent in the sense that if you had infinite data, right? If you have infinite data, the ST that you would get on this time interval would be the grad of log rho Tx on that time interval, right? Of course, the quality, and that's because, you have mass at every time and every x, and you have mass at every time and every x, right? But of course, the quality that you're going to get will depend, on the time that you put here and the decay that you put here. For example, let's imagine that, if the time is finite here, I could just drop this and just put uniform on 0t. But you realize that what's happening here, right, is that if you look at this process, so what is the process that we have here? Is that you take your data points, and then so that's your image. Think about the image. You fade it out exponentially, and you add noise, which has a variance that is 0 initially, and then exponentially fast goes towards 1. Right? That's what's happening. Okay? So, well, it means, for example, that let's imagine that I take t here to be 500, whatever, right? Well, at least in, if you think low dimension, most of the data that you will draw from here have completely lost the data. This guy is totally gone, right? In fact, at that time, the dynamics has completely stopped. The VT is equal to 0. This guy is just balancing this, right? So you need to tune the knobs here and adjust the T there and the weight in such a way that at the end your loss is informative, as usual, right? And there's two things you need to play with, which is that in some sense this weight needs to be adjusted in such a way that when there is some action that's going on with your data, you still pick it out, which is before your image has faded, you need to be able to see what this process, because that's the process that you need to undo, right? That's one thing. And then you still need to keep T sufficiently large, because in practice, whether you use this or you use that, you will not be able to start from infinity and going back towards 0. You'll start at a finite time. But that means that at this finite time, you shouldn't really sample from rho B, which is what you would do in practice. You should sample from this guy, but that guy you don't know. So there's a little approximation here that is being made, which is that in practice you'll sample from this as if it was that, and then push from there. So there's a little bit of a statistical error. But it's exponentially small, the error that you do that.
So that capital T, if it's like a few characteristic timescales of the OU process, that should be good intuitively.
Yes, except that, that's right. Because you see that the rate here is uniform, right? There is no factor D, that's right? So overall, it is a splendid idea. It's very simple, but it's a splendid idea because, just a second, because at the end of the day, it says, instead of trying to kill yourself into trying to construct a normalizing flow by writing what I wrote with this, backward and forward, like in optimizing a loss that is on the final time, I can actually just do this, and I don't need to use the adjoint, I don't need to use the OD for the optimization, I just optimize the quantity which is over there. Okay?
I guess, in practice what you do is you sample a point xi and then you noise it up by sampling a standard Gaussian and taking a combination of a little bit of that point and a lot of that Gaussian. I'm assuming that you only use each point once and you use then, so for each point you sample one Gaussian right, so for each point xi you sample one Gaussian and you get a noisy point, and you don't reuse the same point. You don't sample two Gaussians, right?
So you could, if you could, so if you want to, let's say, forgetting about practicalities, right? One way you could do this is that you fix your data. Let's imagine I use full batch. Pretend I can do that, right? Then what you would do is that you would use the full data set at every step, so whatever data set you had here, right? And you could potentially, once and for all, draw k time point and k realization. So actually, you see that so on these times point, you could draw these guys once for every data point. You'd get n times k value of this. Right, and then that's your batch. It's fixed.
But at each time point, you don't reuse. Like you at each time point, at least you have only one realization of the noise per original point.
Right. So, but you could do something which is different. Yeah, that's right. Yes, but you could do. You can really stochastic gradient descent. So there's many variants of this, which is that even if you keep using the full batch, which they don't do in practice, obviously, but if you had to use the full batch at every iteration, you could redraw times, and at every one of these times, redraw that guy, right? So each time you would redraw on the batch or the mini batch that you used, you would redraw n times k, okay? And you can repeat that. So now it becomes a stochastic optimization. But as I say, in terms of the quality that you will get, that one you're stuck with.
Yeah, so is it the case that n has to be larger than the dimension that these things live in, because otherwise you might depend too much on which particular realization of the noise you took, or?
Yes, I mean, that's, this is all of these things about kind of, what is the effective dimension of all of these things. And these are, trying to assess what's going on with this in practice is actually, quite complicated. I'll get to this in a minute to give the example of a mixture of Gaussian. In practice, when you do it with images, right, at least visually, the image that they create are astounding, right? Now, I mean, as I was saying in one of the other lecture, as a sampler from statistical mechanics, it's a little bit difficult to assess what's the quality of a sample. Like, it's just that your brain is filtering very well, saying, oh, that's a nice image, but making, quality. So they do cross-correlation with their data set and things like that. But I don't know they have measures of qualities that are empirical, where you cross-validate in a way, okay? The fact, like with many other things in machine learning, the fact that it works seems to indicate that at the end of the day, images, the intrinsic dimension of images cannot be that big, which is a strange fact. The fact that, I mean, these ideas with, low dimensional manifold are a bit misleading, right? Because if you have a manifold can be low dimensional and very twisted on itself, which means that it seems that that's what these neural networks are good at finding. But it is not like the standard, hyperplane that we would be used to.
So these things, like it seems that just if the data lies on a no-dimensional manifold, but itself lives in a hugely dimensional space, I actually naively would have imagined that you would still need tons of points, just because there is a problem with because otherwise it seems like still the realization of the particular noise could have a lot of impact.
So I'll maybe write an example where maybe we can try to assess this, right? Because there is something about images which is kind of strange here, and that, I think that's an avenue of research, which is that, of course, the UNet architecture has that embedded in it, but in some sense there is something which is quite strange here, right? Which is that the image recognition is based on this convolutional net that really use the structure of the image in making filtering at all scales and things like this. Whereas here, a priori, you're doing something which is that you're destroying all the structure. Like the way it's done is that you take your pixel, and every pixel is you add noise, right? So there is nothing in here except in the architecture of the UNet that's actually telling that's an image. And yet, it works fairly well. Which is also strange because, intuitively, you would expect that in this RD space, this density, even if there is a density which is not completely clear, should live, almost on a manifold of very low dimension that's going to be spread out into RD, right? This is what this is doing. And then you will have to kind of get it back. In practice, it's work. I mean, that's all I can say. But the basic idea is this.
So I guess the idea is that the velocity is such that if you go backwards, then if you take a random point in Gaussian space, it points you towards the manifold.
Yeah, right. So there's many mysteries here, right? Which is, why is it that this architecture is actually capable of doing that? There is the fact that this loss here, if you just think about it, is a strange loss, because and in fact they have done tricks. There are tricks to to kind of what's called the denoising loss, because if you just use this, there's this annoying factor that let's just think about this on one time slice if the samples were fixed, right? And probably that's why it's a good idea to add noise all the time, is that you can control this term, but this one is actually unbounded from below, right? You can make it if your data set was fixed, this guy can really dig. So it's really I think it's a key to add noise each time you do thing, okay? Now, maybe I can, and then I think I'm pretty much done. And do you have a question about this? Yeah.
So what prevents the S from being very singular, like bunched up mostly towards the times 0 part from that optimization? S of t.
You're really learning this function, right?
If you minimize that loss for
yes.
S, so is S of t that comes out smooth and?
I mean, it's smooth enough that you can integrate these equations and get something out of it, right? Clearly, if you don't have enough data, right, or if you put too much weight at the beginning, you will learn a S that you can trust at the beginning and no longer at the end, or the other way around, right? As usual, you only know that with enough data, if you manage that this guy is a good approximation of this, then you'll get the true S, no matter what the weight is. In practice, you need to adjust it. And we can discuss that later, what would be the optimal weight that you need to put there. Okay, that's because, again, by thinking about our measure move or the density move in the space, there is a natural metric, which is to use the arc length of the path, the rho t. Let's discuss that later, okay? Yeah.
I have a question related to the finite time. Is it true that one really needs to do this with a finite time, because if one would go to infinite time, then all the structure would be gone and this whole velocity field would become 0?
Yes, but that would not be a problem, right? Because you need to think this is something that, I don't know, or you, I mean, for me, for example, thinking dynamical system, I was a little bit perturbed by that. But you need to remember that this velocity depends on time. So even though the velocity is 0, eventually it will pick something because it will lit up and something will still start. So you could go to t equal infinity. Just it's not practical because then the integration would be very long, right? But you could indeed, and let's discuss that after. But you could indeed say, why? Let me just write this down, and then we can discuss it later, right? You could actually tell yourself, why should I use the time? Which time should I use here? Okay, and well, so let me write a formula and see if everyone agrees with that. So if I have, I'm not going to use S because S is the score. This guy here, we can calculate it in the example I'm going to give you in a minute. So if I have the V, suppose I knew the V, which is what we're going to calculate, right? This S here, this is the arc length. So that's the map between physical time and arc length. So it's arc length along this path, right? Because, you know, this is like I have a transport map. This, again, is the arc length in W2, I should have said, in Wasserstein 2, right? This is the way you formulate the arc length. Okay? So that's actually interesting. I don't think that has been done, but it's actually kind of interesting because it says instead of using d over dt everywhere, I could actually go into d over ds. Change the parametrization. That means, you know, that's the weight that I need to put. If you think a little bit about what that is, it's just, you know, this is what you need to put here. You need to do that this becomes ds. Okay? If you do that, you eliminate completely this problem. Because a priori, it converges in a finite, I mean, you know, at the end you have, you know, there's a finite length for this thing. This converge. I can show that to you with an explicit calculation in a minute. Right? If you take, for example, if you take Gaussian, if this was, if this guy, the rho star, is a Gaussian, is instead of being the unit, the normal Gaussian like this, it's just that guy plus a mean, right? So it's, you just take the Gaussian, same variance, but you put it somewhere away. And if you ask what's the total length, so, you know, the total length, so this is the length, it's not the arc length, it's the length up to time t. If you ask what is, you know, you can ask, this is the, if you do this, right, this is the total length of the curve. And if you ask yourself if you have something which is with a, you know, a Gaussian with a certain mean, right, if rho star we can do this later. But if rho star is an n where you have b and the identity, some mean, okay, and you do that like this, you will find that this guy is simply b. It's actually pretty intuitive. We can do that calculation later because it's explicit, right? Which is it's like if you move a Gaussian, the way the Gaussian is moving, we can look at that later, right? If you do this, the way this Gaussian would be moving by this is that you have some variance here that decreases, but there's a variance here that increases and is the same actually, because e to the minus 2t that is bounded by this guy, so the variance actually doesn't move. And the only thing that is moving is that the mean of the Gaussian goes towards 0, right? So that's what. But in this scale, the mean goes to 0 by moving fast at the beginning, and then it's exponential, right? And then it slows down and eventually adjusts itself to 0. In arc length, it would just go uniformly in b, length b, and would be at the end. We can discuss that in a minute. Right? This is a bit of a tangential thing. But let's discuss this idea of Gaussian, because Lenka was interested in that, and let's write this simply here. Sorry? Okay, but I'll do it. I can do it in less than 10 minutes. Watch me.
In time or arc length?
Yeah, right, exactly. I'll just renormalize. And yeah, but there was a question in the back. So,
you just erased the board.
Sorry.
The question I wanted to ask was that when t is large, as you said, you lose the information about the data, right?
Yes.
But somehow you need t to be large for this loss function to capture the whole S hat, right? So we have some sort of a trade-off.
No, because this is where that confused me for a while when I think about this. The velocity field that you are learning depends on time. So at the end of time, it goes to 0 because nothing moves anymore. But you're not using that guide. You're not using this asymptotic velocity field to come back. Right? In the information about the VT that you are learning, right, there is what was the V of t at times that are pre-asymptotic when things were happening. And this information is still there, right? So you start if you were to go to infinity, nothing is happening for a long time because your V is 0, but then it will lit up because it will remember what it was at this initial stage of the diffusion there, and that's when all the action will be happening. So you're not losing the information. I know for physicists this looks like anti-diffusion, right? So it's like. Everybody, you say, I can't do that. I cannot anti-diffuse. But it's not really anti-diffusion that is being done here. It's just looking at you're just looking at this density going one way and then thinking, I could actually, have this movie going in reverse. That's what this does. So there's no loss of information, really.
Yeah, it's not loss of information, but somehow the information is very distributed. So you have little piece of information that is distributed over
That's
the
right.
scale.
So that means what? That if you were to do like this, right? For a Welling-Stern, you would pick a sample, and then in this reverse diffusion, for a while this sample will just do a diffusion. This guy will actually be 0. You'll just be diffusing like an Orschen-Uhrenbeck process. It stays on rho B. But then when you go into sufficiently back towards t equals 0, it will start to create an image. If you do this, there is simply no motion at the beginning. Your samples stay put, and then because V is 0, and then at some point this V lights up, and you're creating a new sample, which hopefully is an image, if that's what you're interested in. Okay?
Can we explain the way that the information is in the velocity field?
Yeah, the information is there.
Different type.
Yes.
It's not transported, so then kind of the fading of the information doesn't make sense.
That's right. So you have, in a way, right, and this is interesting, is that you have constructed, what you learn, you're really learning, the grad log, right? We are learning this guy, right, the gradient of log rho t. right? Which, if you think again as a physicist, right, learning rho, as we learn, from here, it's actually complicated to learn a probability density because you need to be normalized, right? But learning the potential might be easier, right? So, if I think about the problem is that typically this guy, I can always rewrite it like that. This is just, rewriting it as right? So when I take the log, you see, when what you do with this operation, you take the log, and so you end up, taking just the log would not help because you would get the z minus 1. You would get the log of zt minus ut of x in this representation. But now when you take the grad, you kill this and you just have that. So you're learning this, okay? And now there's another thing that's interesting before I move on, which is that score-based is bad. This is a bad metric at a fixed time for a reason which is a bit the same as what I explained in the previous, in the lecture that I just gave, which is that if you want to learn a density which is like this, and you imagine that this height here is much, much larger than 1, right? You'll be able, I will be able to write the gradient here. I'll find the gradient of the potential there. But if there is no connection in between, I will have no idea if I need to put this guy here or put it there. Because I just have the gradient, I cannot integrate. Okay? So that's why the Fisher information, which is this score, is bad at one given time. You should really use the likelihood. But here we are not doing that. We are just learning this guy as a sequence of time, right, to move mass. And that means we only need to know it where it matters. Right? You're not using this, I'm not using the score to sample the distribution. Right? I could do that, right? If I had learned the score, if I had learned this STX, right, which is the gradient of the log of rho Tx, yes, I could use this as dE. In fact, they do. St of x toto, is an artificial, that this is fixed. I could use this as dE. These are tau. It's an artificial time. Tau is artificial time. This guy would sample this distribution at a frozen time. That's a bad idea for the reason that I just explained. Because you don't know the constant in the score. Right? So it's not gonna, you don't know what's going on up there. But this is not what we are doing. Again, we are just moving things like that. Sorry, Lenka. Right? Okay? So it turns out that using the score at one fixed time is a bad idea, but using the sequence of score along this time trajectory works. Okay? And in fact, there are papers where Eman and Song where you can say that it's an elbow for the likelihood. So it actually really works. You can, Okay. Now, I mean, maybe everyone, it's already an hour, so I don't want to. I'll just finish this, almost like an exercise. So even though I think it's a pretty complicated exercise, but if rho star is a Gaussian mixture, so I'll write it like that. Where and the Pj are all strictly positive. So it's a Gaussian mixture. Okay? You can write down explicitly what the velocity is, quite interestingly. You don't need to learn it. Because if this is true, then rho t is what? It's a mixture where each of the weight is the same. So let me try to write it. It's still Pj. And then you simply have that this guy decreases exponentially with time. And then what you have is that you have the original variance is fading out and is being replaced by the identity. Okay? That's the rho t. And you see that what happened is that
So just to type check. Rho T is okay. Rho T
is the time evolved by the Ocean-Beck process.
Probability distribution. Okay,
Yeah,
not velocity, probability distribution.
Probability distribution. So this is the guy.
Probability distribution is basically you kind of convolve the Gaussians.
You convolve the mixture of Gaussian with the heat kernel, if you wish, right? But equivalently, you can just use this formula that tells you that if this is a draw from a Gaussian mixture, well, this is a draw for a Gaussian mixture, which is that has that expression. Okay, and so now, well, okay, so let's put it with a little g here so that you remember that, right? So it's I mean, I'm writing it like it's a function of x, right? Obviously, but if you want to know what is the gradient of the log of rho tg, it has this expression. It's so you're dividing by this guy, and then I'll probably make a mistake here, but and probably the number of mixture, let's call it m to not confuse with the data, we're going to get this, and then it's Cj e to the minus 2t I think it's that with a minus. Right? That's what you get if you do. With the okay. So with the exponential factor that's associated with that, I forgot about that.
Is the square there anywhere?
No, okay, hold on. There is this that I'm missing. Bear with me. Sorry. The exponential factor is a pain. There's e to the minus t that I'm missing here, and this term here is this. E to the minus t transpose, let me write that as a ct. Sorry. I'll write it in. Let's call this guy here cjt, this whole matrix. Then the factor that I'm missing here under the sum is this. Minus 1. I mean, I say this quadratic form. So this is what you get. In particular, if there was only one mode on the Gaussian, this factor here, right? And I missed the normalization factor. Okay, so there's a constant, but this factor here would cancel this one, and you just get that this is a linear velocity field. This is linear in x, right? And otherwise, this is a superposition of linear fields that are weighted by the Gaussian, like that, and then you divide. So what happened is that if you have a Gaussian mixture where the modes are very well separated from 0, where they need to go, the Gaussian, you have a field that's a linear field that are pushing these guys independently, and then at some point they will collide. If there was another one here, for example, right? They will collide, and then something will happen, and then they will recombine. Okay? But you know the velocity field exactly. So now, I mean, now you can start to ask all kind of questions, which is, with respect to the loss that we had done before, can you learn this if you put it in a certain class? Like, for example, you could imagine that the parameter in your network, say I know the number of modes, I could put this in, but I could imagine I put that in, this, and this, say, and try to learn that. How much data do I need? What are the conditions that I have on C, etc., etc. Right? And how well do I do in terms of the flow at the end, right? But clearly, if you do that, it's an interesting exercise, I think. So we're on a project, but the measure of quality cannot be whether you're recovering well the P, the B, and the C. Is whether you're creating good samples.
I mean, maybe you could. I mean, the measure could be how much you're forgetting the empirical thing that you've shown. So just intuitively, if you get less than D points per cluster,
yes,
then the point you're getting will probably very, very correlated with the empirical things that you've gotten, because
yes, that's right.
So
Yeah.
to forget, in some sense, to get something that approximates the mean better than just the empirical points, you kind of want to have at least.
Yes. So you need So you will
cluster.
You will need to be able to learn the B and to have enough data to sample each of these modes independently. But which is interesting, as we discussed before, which is that in the identification problem where you say I'm being given a Gaussian mixture, I'd like to know what is the P, the B, and the C. The difficult case is that when they are all mumbled together,
Yes.
and the easy case is when they are separated. But in this case, it's a bit the opposite in a way, though it's not completely clear what happened when they are mumbled together. But certainly, you need to have enough data points so that each of your modes, you have a good representation of the Gaussian initially, because otherwise it's not going to work.
You want at least in some sense, maybe one kind of sanity check is that if you do this process and now you sample from what you think is P star,
Yeah.
is that the probability you are going to assign to the true mean will be larger than the probability that you're going to assign to the point that you have seen.
Yes. Yes.
Yeah, just one question to clarify. Did you say that if you solve the optimization of that objective on S hat, this is also the log row you would get, grad log row?
If you had a neural network with infinite expressivity and you had infinite data, what this function should be at the end when you have optimized whatever parameter you have is that. I mean, the score that should come out is this one. In fact, what I'm dividing here is the sum with that. I've forgotten the normalization factor, right? So this is the score in this case.
I see, and that optimizing that objective is not tractable analytically.
It is. It gives you this.
With what weighting? Doesn't matter on the weighting.
Doesn't matter. I don't know if if you're asking about the empirical loss, I have no idea. That's complicated. But if you're asking what is the minimizer of the population loss, right, with any weight in time that has mass everywhere, it's that. Because that's if you plug that if you plug this S, right, in the objective, it's 0, identically. And the only possibility for it to be 0 is if S is equal to the grad of the log row. But I mean, it's kind of obvious because here I can manipulate. I have this example is an example in which I know analytically the form of rho t. So I don't need to do the optimization. The optimization would give me that if I were to do it, but right. So. No, I mean, there's many questions, as I said, about actual estimation of this. There are other questions even about, time integration, and that's actually not so interesting, I think. Like, if you have this velocity field, you can certainly integrate that equation to the precision that you want. It's really an estimation problem. Whether does it shed light on, how much data would you need to be able to do this procedure for an example like this, right?
I have a question about the empirical optimization for this. So
Yeah.
basically, you said we need enough points in order to estimate the covariant matrix of this Gaussian mixture. Right?
Yes.
And if we don't have that, then basically it will give you some singular covariant matrix as the maximum, or as the minimum. Is that correct? That kind of if only 2 data points, but you allow also 2 Gaussian, then it will.
So if something bad will happen at the end, because what's going to happen is that so think about the following. If I can start this equation has no problem if I start it. If I replace this by its empirical version, meaning the sum of Dirac, right? But then, if you think about what happened, is that every one of these Dirac is smoothed out very quickly by the diffusion, because you're adding this. right? Which means that even if the measure, say, at the beginning, the distribution doesn't have a density, it acquires one at time t0 plus, right? And then from there on, it's all smooth, and you have a nice velocity field. But if you think about what you need to do now in reverse, right, what's going to happen is that at the end stage, you need to recover this thing that is very spiky, and so this velocity field at t equals 0 needs to become singular, because it needs to push everything on points. Okay? What is done in practice, I'm not completely sure. Maybe they also do another form of early stopping, which is that you don't want to, push the thing too far, right? Or you use that and you put, you play a bit with the diffusion. There are tricks that needs to be used.
How it prevents like remembering each data point what you would do in the general.
I think it's a very good question, and as far as I know, I am not even completely sure whether this is completely prevented. In the sense that, at the end of the day, you get images, and these images, clearly there is a way. So, when you want to assess the quality of the sample that are being created, there's like some sort of a trade-off. You want the image to look very good, but there are images that look very good. These are the ones that were in your data set. So you don't want to recover the one of the data. So you want to have something which is good, but is not in the data set. That's a little bit the trade-off where, the measure of quality is not completely clear. Right? So
In terms of the convergence of the forward and reverse process, it might be useful to use the time-varying step size, right, when you discretize it.
Yeah.
Because towards the end, the velocity will be very small, and perhaps you could afford to take large steps.
Yes, but you can do that if you learn the velocity field, right? This is why. So, but again, I mean, clearly what is being done in practice works very well. So you should take what I say with a grain of salt. But if you want to integrate this SDE, it's actually quite, the numerical tool that we have at our disposal in terms of higher order, accuracy schemes and time varying is actually very limited. It's a mess, SDEs. Here there's a lot that can be done, right? And in particular, you can use, do what you say, which is that depending on the form of velocity field, they are like you can use AKFR4, Runge-Kutta 4-5, which is the combination of two Runge-Kutta that adapts the time step to the nature of the velocity field, for example, right?
It feels a little unclear what this diffusion procedure is buying us over a sort of naive thing. Like, suppose that we have n samples, n empirical samples to work from, and we diffuse them using a sort of calculation like you have in the upper, initially given the upper right here. We can sort of get analytically the true distribution at a given time, right? And we can sample from this directly if we wanted to.
Well, okay, except for one important thing, right? Is that this only works for Gaussian mixture. We don't know what rho t is for an arbitrary rho star. We know to sample it,
yeah,
right? Because you can use this formula. You can use that, yeah, right? And you can, if you want, you can write this down as an integral in a way over rho star, but you don't know rho star. So rho t is unknown, right? Rho t is the convolution by the ETH kernel, which is associated with the, right, of the rho star. But for a complicated rho star, you don't know what it is, so you're stuck. So that doesn't, it is not an option.
Sometimes you also don't even have, you'll never have an analytical form of rho star, like distribution over images, right?
No, but you have a little analytical form for sort of the empirical delta spiky kernel, or the distribution that you start with, that diffusing into noise, right? And you have the analytical expression for this at every time. So if really you're doing a perfect job of running this backwards, like, you could just go and sample this directly, right?
So you're right. I mean, but this is what this is doing. Sorry, I misunderstood. If you think about, you could think about this, right? Which is this, the rho star n that you are using in practice is this. Right? So I agree with you. We have this expression. these are the data point now, right? And then there's 1 over n, sum over n. Then I don't have that, but I just have this. So that is the analytical expression that you have, right? That is correct. So in principle, there is an expression. It's a good point. I didn't think about that, but you can kill this, replace that by 1 over n, and these are the data points, right? Yeah. It's a bit. I mean, if you think about and this guy here is actually simple because it's just the inverse of this identity, right? In fact, this guy is gone. It's just the square of this quantity divided by 1 e to the minus 2t, right? Yeah, it's just, I mean...
So it seems like if you want to sample from this distribution of even t, we can just go and do it.
No, that's right. You have the v. So I don't know, you could potentially use this v, okay? But if you think about this, I think for about a minute, right? This object, the evolution, if you want to think about, I've written something, right? We think about mathematician, it looks great. But then you need to think about it that if you really want to evaluate this, rather than learn, a network point-wise to use the V, right? Then you need to calculate this on every single, you need to make the sum on every single image in your data set, each of which is this very high dimensional vector of, I mean, I don't think that this is a practical object to manipulate. Right?
Is it efficient to sample from this distribution?
Sorry?
Is it efficient to sample, like suppose I hand you a data set and I ask sample from row T, G, that distribution at time T?
I mean, I think that the difference at the end of the day, right, is that what your people that do, because at the end of I don't really do this kind of calculation, but I think that is the difference between, if you phrase it the way I'm phrasing it, right, the way they're phrasing it, you can use neural network architecture to represent your function. That perhaps will be sufficiently efficient, but more importantly, you can use stochastic gradient descent, which is that you can learn with mini batches. Right? What you're actually saying here is that, well, actually I could, just learn the full thing, but that would be like making the optimization with the full batch at, all the time in a way. It's better because if you do optimization with a full batch, you'd have to redo it many times, but still it's not something that I think one can manipulate in practice, right? It's too big. But for a simple example, I agree with you, right? This will obviously have the problem, as you can see, that when t goes to 0, this is singular, right? That's the spike that we need to have. So certainly we would have to rigorize this or kind of end the calculation not at time, but before time t equals 0. But it's an interesting, on low dimensional example, it might be worthwhile to try to do that just to see what actually happens.
It might even just be a good motivation to think about how to regularize this sort of equation in general. If you are worried about any sort of singular sort of things at low t.
Is this
yes.
not the effect of resampling the noise you apply to data points determined from the P star to PT when you're training your model?
But this has account for full resampling, right? Here, right? If you write this down, is like having done online learning on the times that we were drawing and the noise in the diffusion. But what you're stuck with is this, right? The true one should in fact be the expectation somehow of, it should be the limit as n goes to infinity of this. So it should, there's something that's missing here, right? Which is the expectation of the data point. That you cannot get away from. But indeed it could, say, well, I mean, what happened in the final stage? Clearly something bad is happening with that one. Final meaning when you go back. Right? So it might be interesting to look into that. I don't know. If you do, that's another reason why you could learn with a neural network, right? Which is that, at least if you think about it theoretically, in the neural network you can add a regularization term that prevents this, right? Because at the end of the day, what we are talking about here is that, if you don't regularize a neural network and you have infinite capability, it will just memorize the data, right? So you need to do something for this to prevent that, right? And so either you do early stopping or you add an explicit regularization. Here, this is actually maybe falling into the trap that this is, is not in the right function class in a way, at least not at time t equals 0. But I think it's still interesting to figure out what it does. Right? Testing this on take data points in RD, R2, R3, integrate is easy, right? I mean. Okay.
Finally exhausted
I think I'm done, yes.